it was titled as Mathematics of ChatGPT, and so it's about large language models. Let me first check: are there people who teach machine learning, deep learning, AI, neural networks? Venkatesh probably does. No? Okay, are there? Yeah. So you teach neural networks and deep learning. Anybody else? Okay. Yeah, but also that when I say mathematics underlying, I think much of the mathematics will be underlying even in this talk, because it's going to be more a superficial introduction. So let me make that clear. So let me start with thanking Geeta and Shanta and the program committee for giving me this opportunity. What's presented here is a very, not just a simple, but a simplistic account of large language models, which is all I can manage here. I think you need a course to actually learn many of these things properly. The explanations here are principally due to Tim Lee and Sean Trott, AI researchers who are really brilliant at explaining these things. So I really owe it to them for whatever I have learned. Learned in for teaching, I would say, really. Yeah. So what are large language models? And these are machine learning algorithms that can recognize, summarize, translate, predict, and generate human languages on the basis of very large text-based data sets. So this is like one line summary of this whole class of algorithms. Very likely they're going to provide the most convincing human-generated, computer-generated imitation of human language as yet. We haven't seen anything better remotely, I think, in a very long time. So these seem to perform better than all known language models on tasks for which they have not been explicitly trained. And I think this is something that is really a wake-up call, because something is going on. They are trained for a certain purpose, but they're able to do very different things there. This is why ChatGPT turned out to be a major surprise when it came up a few years ago. So we start with the observation that research on natural language processing is decades old. I mean, we are not talking about... So even though, remember that ML is not equal to AI. AI is more than machine learning, and AI is more than all this ChatGPT stuff. And natural language processing algorithms for that have been around for a very long time. In fact, it goes back to the Turing test. Turing in 1950 proposed this idea. How would you say a machine is intelligent? If a human who has a conversation with another being whom you can't see, at the end of the conversation can be as long as you want in a natural language, whichever human language. And at the end of the conversation, you can't tell whether you are talking to a machine or a human being. That machine passes the test of intelligence. So somehow, for human beings, we are very social beings. Language behavior is extremely important for intelligence, right? So the idea is, so that's why we talk about having a conversation, right? I know in APU saying having a conversation is a very loaded thing, right? Okay, I want to have a conversation with you. Well, anyway, so 1964, ELIZA was a program created by Joseph in MIT AI lab. And this was a very interesting program because it talks like a psychiatrist. And it's fun to play with ELIZA even now. It's there on the net. And the original code running. So, it's just, you say something like, I'm feeling very bad today. So why are you feeling very bad today? I have a headache. Why are you having a headache? It'll go on like this. But the point is that you get conned into talking very easily with it. Now, basically to reflect back, but reflect back in a human language. And remember, this is a Fortran program from 1964. Okay. And Weisselbaum, why did he write the program? He wanted to show that the conversations actually are too simplistic and it's users who anthropomorphize the computer. And this is very important. It's a warning coming from 64. It's very important to keep in mind when you are using ChatGPT, right? Remember, that's a piece of software. It's a machine that you're talking to. It's very easy to forget because we tend to anthropomorphize, right? Like I say my pen, I say my inbox, but they're very different things, right? Very different properties. Something that I can hold in my pocket is very different from a file sitting in this thing, right? When you say my Gmail account, right? Your Facebook page, right? You have something in mind, but you forget that we anthropomorphize a lot of stuff. And that is also related to how we. So those algorithms were not programmed to learn connections between words, connections between ideas, any of those things. So what about meaning? This is very elusive. It's also important to realize that until the 1990s, AI research was principally in the academia. And I think AI is one area where you can see research from the academia and the research from the industry are very different things. And I see it in biotechnology as well. And so the questions that you ask are different. And I think it's very important. So there were various methods for representing and communicating meaning in dialogue, emphasis on natural language generation. 1971, MIT, the first program that could take simple natural language inputs that would normally find in human conversation, but to control a machine. Basically, for operating system commands, you wanted to try and use human language. So this was so that machines could develop conceptual understanding of words so that their responses could be more useful. If you're searching for a file, right, it's always a terror when you've got thousands of folders and looking for, I've forgotten that damn directory, right? And yeah. So by mid 90s, language models were used for interfacing with databases. IMDb is one great website, right? It's a great database which has been around for a very long time. The Internet Movie Database, and probably one of the most. And interfacing with these things, the early genome databases, people wanted good interfaces. So natural language research was trying to do these things, right? Games, of course, games, right? I remember that pirate business adventure. One thing in the 90s, people desperately typing text and playing pirates and so on. And inane applications like analyzing car crash reports for liability determination by insurance companies. You should see papers of this kind, right? And today's autocorrect and autocomplete go back to research in that area for text editing, for grammar, for style, all these things. And of course, automatic translation, which was something of a major. So this was something that was spurred on by the Cold War. Actually, a huge amount of defense funding from the US was to translate stuff from Russian to English. And then they found that human beings did a far better job. So they stopped funding a whole lot of AI research because they felt that the automatic translators were not good enough. Human employed Russian experts did a far better job. All this was going on. In the 1990s, statistical language approaches started, mainly because computing power increased. By then, you had PCs, laptops, supercomputers. So computers could learn for themselves. So learning algorithms based on statistical pattern recognition started being developed, and data sets, training data sets were used. I remember in Hyderabad, the University of Hyderabad and IIIT Hyderabad set up this very, very good work, and they did excellent work on natural language processing and especially on training data sets in the 90s. We could compile larger and larger data sets. And so very soon people realized that grammar based techniques were not good enough. Statistical techniques took over, I must say. So it became, I think, by the turn of the century, it was really an interdisciplinary field where people from statistics, linear algebra, linguistics, computer science, artificial intelligence, everybody contributing to wide variety of combinations of techniques. So LLMs come from all this legacy. Now, with the original NLP models and today's LLMs, there is a big difference, but there is also something very common. There are three features that are important. One is a training data set. Then you need some process for learning patterns from a data set and use of some model to generate new text, new data from that, right? Now, this is common to everything. But what changed in the 2000s, between 2000 and 2010, which didn't exist earlier? What is the big change? Which NLP people had no access to before? Social media. Suddenly, when you talk about language data set, right? I think, unimaginable increase in data, unimaginable computing power to analyze the algorithms in this. I think in one decade, I think really things changed. Internet already made a difference, but I must say social media, Facebook, right? And multi-mode data. data which is text, data that is images, right? The ability to look at all of these in one uniform fashion. I remember in 90s, we all used to say, you can upload files, but photos, you see how difficult it is. Movies, streaming, impossible. 5 years later, and today you look at it on your phone. So data suddenly changed enormously. So I think the fact that I remember the work of the Hyderabad researchers trying to get data, trying to get human text, corpus, build a corpus. Here it was free, voluntarily all of humanity was giving it to Google and Facebook, and, you tick all those things, free use by the companies, right? So suddenly they could mine huge amounts of data. And that is why the shift also happened. The research really moved from academia to industry during this period, right? Because these guys were sitting on data. The 6 corporations in the world sitting on practically all of humanity's data. So LLMs are much larger, much larger, you have to say, both in terms of the massive amounts of training data sets and the millions of complex word patterns and associations the model contains, right? As you blink, how many logins are happening in the world? Think about it. When we say huge amounts of data, we really mean something, right? So most classical approaches were rooted on estimating probabilities over classic thing was trigrams. I'll say more general n-grams. The idea is that if you take a sentence like quick brown fox jumps over the lazy dog, which is the sentence that all linguists love. So quick brown fox is something that you recognize as a pattern that you want to take together. You don't want to split it up, right? So a lot of grammatical techniques go into that. So basically subword recognition was the major work of the time. The problem is that if your subword doesn't appear exactly like as it does in the training corpus, there is no way to estimate its probability at all, right? Basically, you're looking at occurrences of certain patterns in a data set, right? And use that to infer empirical probability. From that, you do some. This is the basic idea that is there in all this. In the 2000s, I should say, word embeddings were used, and this dramatically changed the way these algorithms worked. And the central idea was that if you were to call this trigram as a token, you represent every token as an element of a vector space. And this is the first and very important innovation. For instance, if you look at original GPT-2, a cat is, this is actually something that I plucked from internet. So that is actually the representation that it used. It's a vector of real numbers, all, yeah, and some 300 real numbers, right? Why use such a Baroque notation? Now, look at a list like this. Supposing I write Washington, D.C., 38.99, what do you think I'm saying? 38.99 north, 77 west. New Delhi is, interestingly, I was delighted to find that it's exactly, the other side of Washington, D.C., right? Modi should be very happy. So it's 77.1 east, right? So you can see that. And I just use 1, 2, 3, 4 to code the directions and latitude, longitude. Already from this, you can start inferring, like, for instance, like I said, New Delhi is exactly diametrically opposite to Washington, D.C. on the globe, right? So you infer all these things. And you can see that Paris is east of the GMT, whereas London is west of GMT, and so on. So this is the idea that the moment you represent it as a vector, you can code up a whole lot of attribute information. And you can actually use numerical methods to infer certain amount of. This is the very, So for instance, in GPT-2, I was delighted to find that the closest words to cat are dog, kitten, and pet. Okay. Anyway, so it's some representation they have used. So would a vector of 300 numbers suffice to say everything about a cat? That is the representation that we are looking at. Okay. So this idea that words, so that now that they are elements of a real vector space, you can do arithmetic on them. You can do real arithmetic. So Google launched a project. This is also very recent, 2013. And what they showed was very interesting. They showed in that paper that if they look at the vector, so the vectors are done in such a way The vector representation is chosen in such a way that if I do biggest minus big plus small, I get the vector closest to smallest. So you can actually move things around in your vector space in such a way that the position information and whatever norm you are using for comparison can give you information. This is the main idea that Google had, and I thought it was a brilliant idea. Like, for instance, you can easily infer that unethical to ethical has exactly the same relationship as possible to impossible, and so on. But also to man, to woman, as king is to queen. You can infer a whole lot of relationships if you choose appropriate representations, right? Representations matter. Beware. And these are warnings that you have to keep in mind throughout anything that you hear. It also gives doctor minus man plus woman, the closest vector is nurse. That tells you something about the training data set, right? Because it is the training data set that is the world for it, right? So its knowledge of the world comes only from the data set that it uses. So that's extremely important to remember. So, but the problem is that words can have multiple meanings. For instance, a bank could be a financial institution or land next to a river. Linguists call these things homonyms. If I say Sonam picks up a newspaper as opposed to Sonam works for a newspaper means very different things. Linguists call this polysemy. Now, what LLMs are able to do is to represent the same word with different vectors depending on the context. So now there are two things going on. A word is represented as a vector. That vector is, think of a huge vector. And that vector is not the same vector in all contexts. Depending on context, the vector representation can change, right? So that you can represent polysemy. This is also a very interesting. So lot of work in the last, this is 2013 that I'm talking about. In the last decade, a lot of work has gone into choosing the right representations. So that's also very important for people who teach linear algebra, right? That vector representations matter like hell. And they use more similar vectors for polysemous meanings than for homogeneous meanings. So you need larger and larger vector spaces, the more and more context and the more similarities you want to handle and differences. But real vector spaces are good enough for almost anything. And that we know what is there. So, but question is, how is this possible? How can you actually come up with these things? For now, it's important. My point is to say vector representations are fundamental to understanding how language models work. For instance, supposing I want to infer, the professor asks the student to improve her written work. Whom does her refer to? Common sense says it's the student's work. But there is nothing in for a language processor to figure out whether it's the professor's work or the student's work, right? Assuming both are female, right? So this requires understanding facts about the world, and it involves learning. And this is where these are learning algorithms. Now, think of the context for the vector as the dimension of the vector space, right? So it's the dimension of the vector space that providing context information for you. So what does GPT-3 do, for instance? It takes word vectors and it moves from computes with them to provide word predictions. Okay. Every layer takes a sequence of vectors as inputs, one vector for each word. Remember, every word is a vector now. And it adds information to clarify the meaning of that word and better predict which word might come next. Now, remember, for anybody who, if you're interested in language education at all, first thing you learn, what is reading about? Anticipation. Reading is not about coding, right? It's not about adding letters, right? By the time you've read half a sentence, your mind is automatically anticipating what word comes. It's all about anticipation. How can a language model do anticipation? Which information is important? When you have processed the sentence so far, some information is there. Remember, reading is an act of cognition. Vision is an act of cognition. When I see it, when I look at you, I'm getting all kinds of information. The fact that Arindam is wearing a blue shirt is getting into my head. But I don't remember all this, right? The brain filters out enormous amounts, right? And gives certain summary. That's all that is there. So even though it's a physical lens, right? And it's happening physically in a geometric space. Whole lot of facts are being registered, but the brain selects. This is fundamental. Similarly, reading is an act of cognition. There's a whole lot of stuff in that sentence. You read, you forget. Some you are anticipate. This turned out to be the dramatic advantage, and that's where GPT suddenly comes into play. 2017, Google DeepMind put out a paper and they proposed what they call transformer architecture. GPT stands for Generative Pre-trained Transformer. So, the first thing that they start with is that you don't do things word at a time. All these vectors are great, but you think sentence at a time. But within a sentence, you are looking at relationship between words. So it's not trigrams, it's not words occurring together, but words occurring in a whole context. And then a so-called attention mechanism, which is what I call anticipation in a child reading, right? When we read, we have anticipation, they'll call it attention mechanism. It's a landmark paper. Attention is all you need. It's easily become the most cited paper in all of, I think among all these things. Yeah. So Vukash Kaiser was a postdoc who has been in math science for quite some time. So he's there in the second last. For those who have been in math science, you would have remembered Vukash. So this paper, I think really, as I said, this, which is less than 8 years ago, really changed things. So what is the transformer architecture? So this is all from Understanding AI, right? So that's a book. It's also available online. Yeah. John wants his bank to cash and you want to find out what is the next word, right? Probably cash the check, right? Okay. This is the American sentence. So transformer looks at that. Each word is a vector now, right? It's taking all these vectors and then it figures out wants is a verb. That's not easy because wants could be a noun also, plural of a noun. It figures out cash is a verb. It could be noun or verb. It figures out, and what does it do? I have put something in red. What it actually is to transform the vector. It will give a new vector where the fact that wants is the vector for wants is now transformed into a vector for wants that is a verb as opposed to wants that is a plural of a noun, right? So when I say transformation, I mean a linear transformation. Is also some affine stuff is going on. So you do all this analysis, the kind of analysis that you are doing, you're turning it into operations, some linear operation, some linear transformation. And then you have another layer. The next layer has figured out that his refers to John. John wants his bank, okay. And bank here is a financial institution and nothing to do with reverse, right? So it keeps transform. So you give a sequence of vectors, that sequence, so n vectors, you get another n vectors, you get another n vectors. This is all you do. Keep on doing. This is the idea. So the partial sentence as well, okay, what I just explained this. So these new vectors known as hidden state are passed from one transformer to the next in the stack. It's called a stack of transformers. And you keep adding context information. So simultaneously, it's operating in a large dimensional vector space. So therefore, it's having all that context information built into it. This is the important thing that you should keep in mind. Okay. Now, how many layers? Earliest versions of GPT-3 had 96 layers. So we are not talking about 1 or 2. And research suggests that the first few layers focus on understanding the syntax of the sentence and resolving ambiguities like bank, wants being a verb here, and so on. Later layers develop a high-level understanding of the passage as a whole. Now, how many dimensions are we talking about? GPT-3 uses 12,288 dimensions. That's all engineering. Don't ask how the numbers come. Okay. So, what is the goal here? You start with the sentence and you have every word. Let's say if it has k words, you have k vectors, each in this 12,288 dimensions, applied 96 transformations applied to it, and what you get. What is the goal of that? The goal is to output a hidden state for the final word that includes all the information necessary to predict the next word. That's all. I have given a sentence of length k. It then predicts what is the k plus 1th word. That is the anticipation that I'm talking about. They realize that what, as I said, every language teacher has always known. Somehow you can get a child to anticipate the next word. Reading is easy. That's all they did. But that has proved to be the most dramatic. So what is happening inside the transformers? It's a two-step process, the so-called attention step. Think of it as a word that looks around for other words, right? And that have relevant context, and somehow they share information with one another. Then there is something called a feed-forward step, where each word thinks about information gathered in previous attention steps and tries to predict the next word. And remember that words don't do these things. There is a neural network that is doing all this work. So what is a neural network? I will get to it later. So main point is that transformers treat words rather than entire sentences or passages as the basic unit of analysis. They are elements of a vector space. It's just that the vector space has humongous dimension. So the main point of doing that is that if you have 10 words, there are 10 parallel processes acting for you at the same time, right? But they are all moving in this huge dimension, in the vector space of a huge dimension, of common dimension. So that is the real beauty of this way of doing things. So what is this attention mechanism? Think of it as a kind of a matchmaking service for words. Every word makes a checklist. They call it a query vector that maybe here there will be, basically it says I am a word of that kind. I am looking for so and so. Key vector says I am so and so. I have these characteristics. And how do you find the match? Dot product. As simple as that. Dot product does the job. Okay. And of course, the point is that you're taking a vector and forming dot products with a whole lot of them and checking for optimality and picking the best. What is the best and how you do? I'll get to. There, probability has to come in. So once it finds a match, it transfers information from the word that produced the key vector to the word that produced the query vector. So it modifies that vector. So for instance, I have this thing. So the query vector for his says, I am seeking a noun describing a male person. The key vector for John would say, I am a noun describing a male person, right? Remember, it's acting in huge dimensions, so it's describing a huge number of things, right? It says, I am Devakaran and I teach linear algebra and I'm wearing a blue shirt and I'm doing this. Huge number of information is there, right? So network somehow detects these two vectors that they match and apply the transformation. So this is a hydra. I said attention. This is what is called attention head by GPT. There are several attention heads at the same time. And it's happening in parallel in each layer. One head might be looking at this matching pronouncing pronouns with nouns. Another head may be figuring out this bank is a financial institution, homonyms. Third one looks for two phrases and connects them, like saying Donald Trump means it's one phrase and not, very different. It could be completely different things. The word Trump means different things, remember. Yeah. So the network is very complicated. It's not just a parallel network, it's a series parallel network for those who understand what that means, right? Because there is something happening in sequencing. Sequencing is very important because the results of one attention layer are inputs to the next layer. So GPT has 96 layers with 96 attention heads each. So it performs 9,216 attention operations. Each time it predicts a new word for one word. So the enormous computing power that you're talking about is unparalleled. So then I told you that the second one thinks about words. What is that? It's a feed-forward network that tries to predict the next word. Okay. So it analyzes each word in isolation. That's true, but it has access to all the information that it has previously copied from the sentence, but earlier sentences, and from the whole training data set. That's the point. It has a huge number of connections. It's a neural network with large number of connections. So here's the thing that GPT-3 uses. Input vector is a vector with 12,288 values. Okay. The hidden layer has 49,152 neurons. Output vector has, again, 12,288 neurons, and then output vector has these. So as a map, you are looking at something that's going from a map from R to the D to R to the D, where D is 12,288. That's clear, because these are all linear transformations being applied. So it's a very large one. So I've showed you a calculation to show how you get that 116. With just the feed-forward network of GPT-3 is got 116 billion parameters. And an overall total of GPT-3 is 175 billion parameters. That's huge, but that's nothing compared to today. Beijing Academy of AI has put out that thing which has 1 trillion parameters. And they're all like outdoing each other on, I can do so many. DeepSeek has shown that you don't need that many. That's also another game going on. So what is very nice is another paper here, and this is, look at the date, April 2024. I'm talking about, these are all recent stuff, right? So these things actually, they show that they actually do vector arithmetic. Okay. So I'm saying they are doing some transformations in some linear transformations, right? What is it that they do? So for instance, they found that feed-forward layers that I talked about do exactly the same kind of vector arithmetic that I talked about earlier. Remember that smallest minus small, right, plus big is equals to biggest, that kind of thing. So I'll skip this demonstration. Let me. So prompts, we also find that when you use GPT, the prompt actually changes things, right? So what is going on? Actually, the feed-forward network actually gets trained with every prompt. And that's what it points out. Basically, every time you are giving a prompt, you are modifying the feed-forward network. That's the important thing, that it has a feed-forward network, and the parameters are being adjusted with every prompt. So feed-forward network is the thinking one. The attention step is the reading one. That's how they have divided the labor. And then there is training, right? Training the model. So the prediction of a newly initialized language model is essentially a random number. You have to really see an initialized GPT-3 will give all kinds of crazy words. But as the model sees many more examples, hundreds of billions of words, these weights are gradually adjusted and the network gets more and more stable with its parameter values, and then it can make better and better predictions. So it's a little bit like this. I was thinking of an analogy. Okay, something like this. You come to GR, there is a shower faucet, nothing that says hot or cold. So you expect left to be hot, but you also had nasty experiences in the past. So you gingerly move it around, test it, and you decide. That's pretty much what happens. You start in some random direction. Remember, they are doing linear transformations in some affine. Yeah. So you move in a random direction and thoda adjust karo. That's all you keep doing. Sounds easy. Suppose that you have 50,000 faucets instead of one. And there is a maze of interconnected pipes behind the faucets. And these pipes have a bunch of valves in them as well. What would you do? How would you adjust? Well, what you would do is maybe you have an army of intelligent squirrels which goes along each pipe backwards and adjusts each valve. Right? They find along the way. Something like that what happens in a neural network. So what it does is there is a forward pass where you are adjusting and testing. And there is a backward pass to go around. You have figured out something that you go and change, right? Along for every example. Now, this whole thing gets very silly if you take it too literally. But remember, computers can and do operate in this kind of scale. The difference between you and the computer is that it's not faced by 500,000 faucets. It is not faced by that maze of pipes behind. That's all that's going on with a neural network. So OpenAI estimates that it took more than 300 billion trillion floating point calculations for training GPT-3. That tells you about the kind of compute power they used. How can neural networks remember? Is a question, no? I said training data set you can remember. Every prompt it can learn. How can it? Here is John Hopfield, who showed in 1982 how neural networks could model associative memory. It's a little bit like this. You hear a song, you remember some event. This happens to all of us, right? So he gave a formula that uses the values at all nodes and strengthens and the strengths of all the connections at the same time. And he was awarded the 2024 Nobel Prize for Physics for these. How can a network act as memory? I'm walking down somewhere and some window, I can smell sambar, right? And immediately it triggers certain childhood memories, right? So this is what we call associative memory. So he used to work on magnetic spin and he applied the same idea to neural networks. Simultaneously, you can look at the spin of several magnets and then look at a spin network. And that's exactly what he applied. So every input adjusts connections of all the values. That is the important idea. And this configuration that you get codes up a memory state. And this memory is retained. And neurons affected by a smell and those by a song can trigger each other. It's very likely that that's what is going on in your brain. So what are neural networks? It is a very simple thing, some inputs and some weights. And then you sum all of them, right? And then apply a threshold function, right? Sounds very simple. That's all. But then our question is, how do you determine the weights? So for instance, suppose you are looking at an image, the image of a baby in a pram. And those are the inputs, no pixels from some camera. Now, what I want is one neuron to fire to recognize a baby, another for pram, one for the lamppost next to the pram. Maybe in another picture, I want one neuron for cat, one for the baby, none for the baby in the other one. Yeah. So this is what training actually does. Okay. So training is one. What is all the training from data sets? It is about adjusting the weights. Remember those squirrels? That's what they do. In training modes, you send signals back and forth from the input to the output and output to the input, saying this is what I found, and this is called back propagation. So there is one. So these things are interconnected in such a way that you have an output vector. For training, you are also given a target vector. You compare them. There is a kind of error that you can look at. Based on the error, you go and feed the values back and adjust the weights. This is the idea. And so back propagation leads to something very clever because neural network can run forwards as well as backwards. So now I put signals at the output layer that correspond to a car and a baby, and you can get the pixel configuration of a baby driving a car. This is what generative AI is all about. You have an image that was never presented to the network before. People are very shocked that this was not in the training data set. How is it doing something new? The whole phrase generative AI is evoking a lot of, that's all it's doing, right? It's able to look at combinations that never existed. Remember, the combinations it's looking at is in that 12,288 dimensional space. We don't know what to even think of all this stuff, right? So this is what we refer to as generative AI. When we speak of imagination in AI, the underlying process is something like this, right? Of course, I'm being crude about it, but not excessively crude. It's only this sort of stuff. Problem is that some states are, I only said this is how it does. But how do you say one state is more likely than others? And depends on how components can coexist. And this is Geoffrey Hinton, and he showed how you can use an equation due to Boltzmann. 1985 paper, the Boltzmann machine, it learns not from instructions like the training one, but simply given examples. You don't tell the network what to do like you do in programming, but you only give examples and counterexamples. Again, he got the 2024 Nobel Prize in Physics for, and these are the things that made ChatGPT possible. So, children, we see this with children. Very young children can point to animals and, with a few examples, they know, right? No diagrams, no concepts, no explanations, no theory, no assessments, no fancy pedagogic techniques, right? You enter a room and you notice something has changed. This is the kind of learning Hinton brought in. The main idea is a visible layer and a hidden layer. Imagine meeting a friend sibling and you immediately see that she's related to your friend. So it's about probabilities and estimation, and this is something that you can build into networks. And Boltzmann's equation does the job. That's all that. So neural network, I think I will take a little more with this. I'm not sure. Yeah. So there is input layer, hidden layers, output layer. And they work with many layers. I already told you about. Yeah, I think I can skip these things, right? So the more layers you have, you can do something more complex. That is the idea. And the architecture of neural networks is like from an image, you go on applying various maps. That's all. At this point, there's not much you can do. Only thing is, the additional thing that I'm bringing in is whole lot of sampling is going on. You are not only performing affine transformations, right, in a vector space, but you are also sampling along the way. This combination of these two things dramatically changes, right? Yesterday, I think I was talking with Shobha and talking about linear algebra and probability and how we need to, combine the two in our thinking. And this is actually something that neural network people teach you. You really need to think probabilistically in vector spaces. We are not used to doing that. So I'm not going to give you the full blow by blow thing of all of these things you can set formally in appropriate space. You start with any finite set, you're talking about sequences over that, and you can talk about lifting of functions point wise. What is tokenization? The token idea. For every alphabet sequence, you produce a token sequence. But you are doing subword. You are not looking at point wise, but you're looking at taking subwords and generating into tokens. So these functions are a bit complicated. What is this idea of an embedding? Embedding is you are taking tokens and mapping it into some Euclidean space such that you are I'm right. So the norm is also up to you. You can use different norms for similarity measures. And there is a lot of work that goes on into coming up with the right norm for the space that you're working with. And then there is this positional encoding that actually tells you where you are in the sentence because the order matters. And that's also very interesting. So you take whatever is the position and you put some weight. Okay, that's p. The little p is a kind of some prescribed injective function, typically a sinusoid. Why does sinusoids work? That's also something interesting to study here. And what I call transformers is a composition map of this kind. It's basically a neural network that takes a sequence of vectors and produces a sequence of vectors, right? And it has layers, let's say, and each has a attention map, a normalizing layer, and a feed-forward layer, and that's it. And remember that everything is composed with identity. That means you can skip the whole thing and go. This is very important because you go, forward, backwards, ability, and you keep skipping steps as you like. And this is very important because GPT loves to skip steps, right? So what is this? And this is where the probability stuff is coming. I told you only about attention and feed forward. There are these normalizing layers which turn all the things that you are doing into probabilities. There is some diagonalization going on. You can see the classic variance, all these. So all the vectors are always normalized. So finally, you are always going to, the vector values are always in the real interval 0, 1, so that you can interpret them as probabilities. Okay. So whole lot of stuff is going on. And then what is the feed forward network? It's some particular weight matrix and some bias vector. What are these? And then there is this, of course, for a network, you need an activation. You remember the threshold function I was telling you about? What is that? It's the standard Gaussian cumulative distribution function. So why do these things work in combination is a huge mystery to solve, right? And so, okay. I told you about matchmaking. What is that? I told you it's a dot product. It is a dot product, except that it's a dot product of, outputs of certain affine transformation. So, you're taking these, and so the query vector and the key vector that I told you about. And this is also autoregressive. Regression is also coming. So it's fairly clever combination of many things. That's about all I can explain right here. And normalize further to probabilities. And they are all this. Okay. And then there are these final prediction heads. So you translate it all into a probability simplex, and from that you get the numbers that you want. I would say that's basically all I can say, right? So this is very complicated. I just wanted to say that the mathematics is easy to see, but this is not something very easy simply as, okay, n-dimensional vector, this particular affine linear transformation, that sinusoid, this distribution function. You can only get a glimpse of all this. To actually study it, you need to take a long time. So, there is entropy loss, there is derivative, stochastic gradient descent, del function, everything is coming in, right? So, a lot of, so how does the neural network train, right? What is the iteration procedure by which it stabilizes to certain parameters, and that's something you can actually explain using calculus, what is going on. Okay, so let me get on with has AI arrived? In 2023, there is this paper that they wrote. They called it Sparks of Artificial General Intelligence, because they thought with GPT-4 it has really arrived. The examples are impressive, but the claims did not survive closer scrutiny. Today, DeepSeek shows much better ability to learn mathematically. I want to take an example and show, but let me skip these things. It's not important. Because if you play around with GPT, you will see more of all these things. There is a very nice study that I want to tell you about. Education is probably where you're going to see the biggest impact. The key appears to be a shift away from imparting knowledge per se to developing skills relevant for an AI based economy. This is the noises that are coming from policymakers. What does it mean for education? We don't know. In all likelihood, the new system will aim towards personalized education, departing from the quest for uniformity that has characterized education systems ever since the Prussian reforms. Right? There is a certain, from the Industrial Revolution and Prussian reforms days, we have seen a certain shape of public education, and I think that's in for a big change. From the rhetoric of enhancing teaching, it is but a small step to move to a tactic of offering bot teachers. And these are probably what the things that we should. Even this may not be a great disaster, but remember that LLMs do not come from the state. These come from some 6 corporations in the world, right? And what about LLMs to generate mathematical proofs? The likelihood of producing a correct proof diminishes exponentially with increasing text length. You can prove this. There is no problem with that. But the thing is, LLMs turn out to have good accuracy in solving computation tasks when asked to skip intermediate steps, and that's very good. And maybe and they can also probably construct valid proofs for questions different from those that you post. So what? You've learned new proofs, right? Maybe we can make use of it that way. They may prove a theorem under stronger assumptions than stated without making it explicit. It's true. That doesn't answer your question, but you can learn something in the process. People have shown these very interesting things also. They struggle considerably with arithmetic problems, but this is also already changing. Wolfram Alpha has introduced ways of bringing arithmetic into LLMs. Now, last year, there is a team of mathematicians who did a study from Oxford, Vienna, and Caltech together. They used actually exercises from Rudin, Munkres, and Darret and all that. They gave the system proofs with gaps in it, typically from algebra and calculus. And they gave questions like, what's a Banach space? Or how is a complete normed vector space called? They also used it for its symbolic integration. And they wanted to see the performance in all of these. And basically, it worked well on definitions and inverse definitions, struggled with hard exercises from these books. And they did simple computations, and user input had a positive effect, by which you change the prompt slightly and it actually learns from that. And they did very well in finding gaps and proofs and filling them. So they point out that maybe, and these are very good, these are mathematicians who have been doing mathematics all their lives. And one of them says that I've never used technology in anything at all, and suddenly, using it. Maybe this is actually useful. I don't know. LLM interfaces are being developed for tools like GeoGebra and Mathematica and so on. LLMs are being used to add interaction capability to math videos, right? And the personalization bots are being developed for teaching calculus and other specific subjects. A huge amount of work is going on. Within a very short time, EdTech is going to bombard us with lots and lots of software, right? I don't know whether we are even remotely prepared for what this stuff is about. So Google started something in 2017 with the publication of that paper, Attention is All That You Need, right? Where they showed the transformer architecture. In 5 years, ChatGPT came, DeepSeek has come. Now, the underlying mathematics basically is just linear algebra, probability, and computing. And DeepSeek has already shown with other classical AI techniques like reinforcement learning, you can do much better. Alpha geometry, this hybrid of LLMs and classical theorem proving, can solve silver medal level Olympiad problems. That was last year. I have no idea where they are now, right? Yet, yes, every year these papers are showing more and more things, right? So we need considerable experimentation to assess the potential and desirability of using LLMs in mathematics education. I would like to stop with that. Sorry, I went on longer than I intended. Thank you.